watching The Morning Show from your local news leader.
Well, it's time for Wise Guys Wednesday.
U of I physics professor Nadia Mason is with us now with quite a setup already.
Yes, Nadia, I'm very excited. Wise woman, what are we learning?
Okay, today we are learning about quantum physics. Right? And it sounds really, people feel like quantum mechanics is obscure and something not relevant, but it really is. And I'm especially inspired to talk about it today because the National Quantum Initiative was signed into law just last month. It's a $1.2 billion initiative that's designed to support research and education on quantum devices that use technologies for using quantum mechanics, basically.
Sure.
Very good.
And so that's a lot of quantum in there,
I was
right?
just gonna say,
quantum devices.
It's a lot of quant.
That encodes information in quantum mechanics, basically.
Okay.
It's a lot of quantum. So it's a hard thing because even though quantum is really relevant, clearly for future technologies, 1.2 billion for technologies, it feels like something that we're not familiar with in everyday life.
Yeah.
Right?
Sure.
And that's because quantum deals with things at the very smallest scale, like the scale of individual atoms. And so it's not something we see, but it's something we use and hopefully use more of in the future. So in honor of the National Quantum Initiative, I'm going to talk about one of the fundamental tenets of quantum mechanics.
So excited.
And that is the idea that matter can be both a particle and a wave at the same time. And if you just think about it, it's weird, right? We have particles, and this is, a golf ball is a particle, and we have waves like water, and these are extended over space. Now imagine they can be both at the same time. It's really outside our everyday experience, but that's what nature does.
Sure.
Okay, so we're going to use the example of light. Now, light
Excited.
is a wave, right? We know that light is a wave because it can interfere with itself. So for example, here I have just a laser pointer. Can you show inside this box here? So I'm just going to, there's a
Green
light.
light.
There's a green light. Okay, and now I'm going to put it through a slit. And basically, light waves can add to each other, and they can pass through each other, and they can interfere with each other. So if I just put this light through a slit,
And there's a small cut in the middle of the paper plate.
there's a
You
small,
can't see it, guys.
small cut in the middle of the plate. But actually, I'm going to do this is a little easier. There's a small cut in the middle of these, and it's a little easier to see. But what you see there is,
Kind of a...
see those patterns appearing?
Yeah.
Yeah.
See that? There's lots of light and dark patterns. That's the light, so you get light, dark, light, dark. That's because the waves are adding to each other. They're adding and subtracting, you get light and dark patterns, right? That's how you know that light is a wave. Just like, here's water waves. You can show an example of water waves, right? I can you can show the water, right? Light makes it a little easier. If you do an overhead on this, you can see I've made a wave out of the water.
Right.
Or if I've two waves, you can see there's like a pattern there that is formed, right?
Yeah.
That's what we're creating with the lasers. That's how you know things are a wave. So light is a wave, and we're comfortable with that.
Right.
Okay, so now I'm going to be Einstein. I have the crazy hair. I'm going to make the mustache. And then,
I should have
I know, I was thinking, where am I going to mustache? Be Einstein. I was going to get a jacket, but okay. I have something even better, which is over here. What I have is the experiment that won Einstein the Nobel Prize for showing that light is actually a particle.
So cool.
Crazy. So this is the same experiment that Einstein had. So what I have here is light of different colors, and you can't see it here, but maybe you can show it on this side. There we go. We have green and ultraviolet, and the light is going inside this box. It's hitting a piece of metal like this, and then the light is bumping electrons out of the metal. So it's like the light comes in, and it hits the metal, and an electron comes out. That creates a voltage, and you can read that over here on the voltmeter.
Okay, so this is the meter right here.
That's the meter, right.
So we just talked all about how light is a wave. How does this demonstrate that it's a particle?
Okay, good. So what I have here is I'm showing that if I shine green light in here, we get a voltage of something 0.996 volts. Okay, and then if I move it to shine violet light in there, it goes up to 1.5. So the energy of the electrons coming out depends on the color of the light. And that's totally not expected with waves. The color shouldn't matter. We call it the frequency. That shouldn't matter with waves. So it tells you that there's some energy coming in of something that determines the energy of these coming out that seems not to matter. It wouldn't matter for waves. So that shows you it's a particle. In addition, if light were a wave, then the intensity of the light would determine what the energy of electrons coming out. But I can take something that blocks some of the light here. You can read the voltage as 1.547 volts, and I can block some of the light, and it barely changes. Okay, and I blocked a lot of the light here. I blocked 80% of the light, actually.
Because the same electrons are still coming out.
Exactly. The same electrons are still coming out independent of the intensity of the light coming in. So that shows you that it's not a wave. It means that there's some energy that some particle comes in at, that only if it has enough energy, it knocks out electrons with the same energy. The energy coming in determines the energy coming out, which is, again, doesn't matter how much the intensity of the light at all.
So is it both wave and a particle?
Yes.
Yes, it is. It is, and that is the fundamental crazy thing about quantum mechanics. Something can be both a wave and a particle. And just how crazy this is, I can take, I made a big slit here, okay, and I can take what we know of as a particle and throw it at the slit, okay. And it didn't.
That didn't work.
It didn't work. It didn't interfere.
You're right.
And I put these two particles together, and they're not combining, right? So in our everyday life, it seems like this shouldn't be the case, but it is completely true at the atomic scale. Things are both particles and waves. And then you get these really crazy implications of quantum mechanics. It means that particles like electrons actually spread throughout space like a wave. Right? And waves like light actually act like particles. And that allows us to use quantum mechanical properties like the spreading waves for devices like in the National Quantum Initiative.
It's a different world down there.
It's a different world down there, right?
You are both
exciting.
Einstein and Nadia, apparently. So thank you so much, Nadia.
Thanks, guys.
So much fun. You guys send us your questions for our wise guys and wise women. We want to know those. Go to our Facebook page. Let us know what you want to learn about. Coming up, we're going to get a check of the forecast.
Be right back.